Welcome everybody. For those of you that don't know me, I'm Francesco Ciccarello. I'm leading the Hybrid Quantum Circuit here in QSE. And today we have the pleasure to host Francesco Ciccarello. Francesco is a professor at Università of Palermo in Sicily, in Italy. And today will tell us about atom photon bound state. He's an expert in waveguide QED, and he's going to stay with us this afternoon and also tomorrow morning. So if some of you are curious to have a chat with him, just please approach at the end of the seminar, and then yes, we can arrange, okay? So please, Francesco.
Hey everybody, thank you so much, Pasquale, for the invitation. And as Pasquale asked me to try to be as pedagogical as possible, and I made an attempt, so I hope we will like it. I'm not sure that it will be successful. Probably pizza will be more tasty than this talk. So this talk is mostly about atom photon bound state in modern quantum optics, when the main focus will be the connection between atom photon bound state and the variance-free interaction, so-called. So I will assume a very basic knowledge of cavity QED, very basic like James Cummings model and Limblom mass derivation, but even though I might recall it very briefly. So let me just say a few words about the environment where I work in. We are a big quantum theory group in Palermo, Sicily, southern Italy or northern Africa, depending on the viewpoints. We currently hire many postdocs, so the group is growing very much these days. And we deal on a number of research lines, including a number of subfields of quantum information theory and quantum optics, condensed matter as well. So, traditional quantum optics, two long-standing systems people looked at over the decades are how atoms emit in free space, and another long-standing paradigm is how an atom emits into a cavity. But the message, somehow take-home message from the cavity part, is that changing the electromagnetic environment affects the way atom-photon interactions take place, including emission properties and other stuff. Now, based on technological advancement occurred in the last maybe 10 or 50 years, and here we have a very brilliant experimental group, and groups actually, it is now possible to engineer photonic paths, which are quite more sophisticated than just a single mode cavity. And a paradigm in this respect is a couple cavity array, where you have a set of one mode cavity, which are now coupled to one another with this coupling rate, which I'll call J throughout, and I call this guy hopping rate, because it's the rate at which a photon can hop between two near stable cavities. And in this case, you can now manage to couple locally atoms, where atoms are meant here in a generalized sense. It can be an atom-like system, like a two-level system, which could be like a superconducting qubit or a quantum dot, or a number of other things. Here in this case, here APFL will be a superconducting qubit, so quite a big, larger system than an atom, but it essentially behaves like a two-level system. And if you have a lattice, then a lattice will feature a band structure of the energy spectrum. And it's interesting to ask, if I now park the atom frequency inside, for instance, a bandgap, how does the atom interact with my photonic lattice, which now has a band structure? Just to give you an idea, these are two instances of our experimental setups. This one is actually a joint work where I included Pasquale and Marco Scigliuzzo, and this was done in Chalmers about 3 or 4 years ago. And here they can engineer, fabricate two atoms, actually two superconducting qubits. You see coupled to selectively and locally to two cavities out of a 22 couple cavity array. And here you can see this quite clearly. But you can also engineer now 2D lattices like this one. This emulates a so-called Hopper-Hofstadter model, which is kind of discrete version of the quantum Hall effect system, where you can couple an atom to an edge of this system, and this was done in Chicago, I think 2 or 3 years ago. And another important novelty that came out in the last year is that now you can also, in certain experimental platforms, in particular CircuitQED, including the labs here at TPFL, they can now couple very easily a quantum emitter like a superconducting qubit to know locally. That means that, yeah, I mean, in this case, this is a continuous waveguide, but this can also be done with a couple cavity array. I mean, you can easily couple the quantum emitter or atom if you want simultaneously to more than one cavity. Okay, this is interesting because these are non-local coupling that brings about some interesting effects compared to a standard point-like atom, which I will discuss toward the second part of the talk. Okay. Let me just review here some cavity QED. I told you that this is a long-standing paradigm, but it is still conceptually very important and actually still a very active line of research. And in particular, I want to review here what is called by some people the dispersive regime of cavity QED. It is also a good chance because one main goal of my, well, even the main goal of this talk is introducing atom-photon bound state and connecting them to so-called decoherence-free interactions between atoms, and which occur in the dispersive regime. So that's why I need somehow to get you familiar with the dispersive regime. Right, so you have an atom in one more cavity. This is the cavity frequency. This is the atom, the top one is the atom frequency. You have a detuning delta between the two. And this is the standard, James-Cummings model, where you can, where you see I have, this is also a notation that will be used throughout. This G is the atom field coupling strength, and you see that I'm making the rotating wave approximation, which I will also carry out throughout this talk. Okay. You can set the atom free on resonance with the cavity modes. In that case, the detuning is 0, and then you have, you ask how the atom emits into the cavity. Atom in free space, when you excite an atom, bring it in the excited state. If it is in free space, it just decays exponentially, right? Because in free space, right, photons departs away. The atom it decays, photon departs away. There is no way for the photons to return to the atom. Okay. In a cavity, it's already intuitive, right, that if an atom emits into a cavity, and then there is a way for the atom to reabsorb it. And actually, this is quite a striking regime because when you have perfect resonance between the two, you prepare that this is the atomic the blue curve is the atomic excitation, the red is the photonic one, and with the cavity in the vacuum state, you have something which is somehow opposite to the spontaneous emission, because in this case the atom emits, the atom releases an excitation, the cavity gets excited. There is even a certain time at which the atom has fully decayed to the ground state, and you have the cavity in one photon. You have one photon in the cavity, and then the atom, you see at a later time, can fully reabsorb the photon, and the cavity again is in vacuum state. So you have a completely different regime compared to spontaneous emission, because here the thing is fully reversible, right? With spontaneous emission, the atom emits the photon is irreversibly lost. Here, you can even reabsorb back the photon and then emits again and reabsorb again. Okay. This thing depends on the detuning, because here you see that energy excitation between the atom and cavity mode is maximized because you are on resonance. What if you are off resonance and you set the detuning a little bit larger, now comparable to G? You see that the atom still gets excited a little bit, and the cavity is still excited a little, populated a little bit. But now the atom is no longer able to fully decay to the ground state, and of course the atom in the cavity will no longer be fully able to get a full photon. And that's why you are now getting a little more and more off resonance, right? An interesting regime, which at this point may even look kind of trivial, is the so-called dispersive regime. When the neutrino gets really much larger than G, in fact, it's enough that it's a little bit larger than G. Okay, what happens is the atom almost doesn't decay, and the atom in the cavity almost never gets excited. But actually, you see that there are these tiny oscillations here. Okay, and this can be explained. Some people explain this in terms of virtual photons, like a second-order process. Because when you are off resonance, first-order processes are inhibited because you are off resonance. But then you can have, then the atom can emit a photon, okay, for a virtual photon for a very short time, and reabsorb it immediately. And this is the reason why you see these tiny micro oscillations. And correspondingly, you see that the cavity gets a little bit excited in an oscillatory way, corresponding to this quick creation and reabsorption of virtual photons. Okay. So long as you have one atom, I mean, this gives rise actually to some interesting effects, but even more spectacularly, this is the case where you have two atoms in this regime. So let me now consider two atoms in a cavity. Basically, this is the same kind of Hamiltonian with just two atoms. I'm assuming that the coupling of each atom to the cavity is the same. Okay, so the two atoms are fully identical, and this is what you see under resonance. So you see that the blue one is one atom. So I'm starting from the state where one atom is excited, the other atom is in the ground state, and no photons in the cavity. Okay, and so you see, you don't see this. Do you see another?
No, it's not visible.
So that's not because I'm colorblind.
No. It's really not visible.
I feel relieved. There should be another curve here showing the excitation of the other atom. Okay.
So just one minus the blue.
Yeah. Not one minus, because here you are on resonance. You also have the cavity regulation. Okay. But what happens here is that there are one atom gets excited and can excite both the cavity. The cavity can excite also the other atom. Okay, so what you see is that population of the first atom also shows oscillations, and actually times at which also the other atom gets excited. But you see that the cavity is never is still on average it has a certain energy. Okay. And then when you start increasing detuning, you see that the cavity gets less and less excited. That's a pity that you don't see the. Okay. And then at some point, when you go in the dispersive regime, now with two atoms, something interesting happens. Because once again, you see on here the time scale is larger than here. You see that here once again you have almost negligible excitation of the cavity mode, corresponding to quick creation and absorption of virtual photons. But now you see that you don't see actually, because here you should see the other. Maybe if I this way you can.
No, it's not.
No, sorry. Okay. What you would, so if you plot the same curve for the other atom, you will see now that it goes like this, really like one minus this curve. Okay. And again, you see that if you look carefully, you see these tiny oscillations here. Okay. So you see that the difference compared to the previous case, which brings about a very interesting effect. In this case, when you're off resonance, an excited atom can briefly emit and immediately reabsorb a virtual photon. But now you have two atoms, right? So one atom is in the excited state and the other one is the ground state. Once again, the first atom can quickly emit a single photon, which can now be either reabsorbed by itself, but also can be absorbed by the other atom. Okay, and this gives rise to an effective interaction and excitation transfer between the two atoms. Okay. And this, in fact, gives rise to an effective interaction between the atoms, and it's as if this is the remarkable thing. It's as if the two atoms were directly coupled to one another. In fact, this interaction is mediated by virtual photons, but it's as if they were directly coupled to one another according to this Hamiltonian here. Right? And this is the coupling, the strength of the effective interaction. We typically scale as the square root of the coupling strength over the detuning. Okay. I want to make a comment here because this will be useful later. You see that if I now have many atoms and they're all coupled with the same strength to the cavity, you will still see that you still have a generalization of this guy with all pairs coupled with the same strength. Okay? So the strength of the interaction in this sense is the same for all atoms. So in some sense it's long range. I mean, there's no like a thing like where only near closer atoms interact with one another. There is like what some people call all-to-all interactions between the atoms. Okay? And one question then people ask is if there is a way to engineer such dispersive regime, decoherence-free interaction between the two atoms in such a way that the interaction potential between atoms is more interesting, has a more structural shape. And this can be done with the coupled cavity array. So let me just for now just talk about one atom coupled to a coupled cavity array. This is the Hamiltonian. Now I have many cavity modes. These are bosonic ladder operators for cavity mode N. And this is a standard tight binding Hamiltonian where J is the hopping rate, and this is the coupling of the coupling of the atom to cavity 0. So without the atom, the cavity, as I already anticipated, features an energy spectrum which is a single band. And the width of this band goes like the photon hopping rate J. And now you can tune the atom at off band. In this case, delta will denote now the detuning from the upper band edge of my lattice, which lies at 2J. But you can also tune omega 0 inside the band. So here I'm showing 4 cases. In all of these cases, I'm taking G to be much smaller than J, what you can call probably weak coupling regime. Well, it actually depends. Generally, you can call it weak coupling regime. So G is much smaller than J. So if G is much smaller than J, and the atomic frequency lies here, right at the center of the band, then the atom will undergo exponential decay. You see now a difference compared to cavity. Cavity is just one mode. Like here, I'm assuming that you have a thermodynamically large number of cavities. Okay, and in fact, the entire coupled cavity array behaved like a standard photonic bath in this case. Okay. But it's interesting now that when you move the atomic frequency closer to the edge, actually on the edge, you have now this behavior here. So the atom decays, you have oscillations, but now the atom never gets fully excited, and it actually at large time converts to an asymptotic value, which is finite. And this is also true when now the atom sits out of the band, the atom frequency sits out of the band, but now you see that the asymptotic value is larger. And at some point, of course, when the atomic frequency is very far from the band, right? At some point, it's clear that the atom will not decay at all, right? Because photon modes only live here, right? And so if I have the atom off the band, the atom will couple to modes living in the band only off resonantly. But then if the tuning gets really, really very large, then it will not couple at all. Okay? And in that case, the atom just does not decay, because there are no modes to decaying. But if the detuning is still not too large, like in this case, where here we are already in the beginning, this 2.2, you see something similar to what we had in a cavity mode, like in the dispersive regime, okay, where you remember the first blocks. Okay, what about two atoms coupled to a coupled cavity array? I wonder whether, so the dispersive regime, the dispersive regime here is once again when the coupling strength is much lower than the detuning of the atom now from the band edge, okay? You can now wonder what happens if I now have two atoms coupled to the coupled cavity array in the dispersive regime, whether again I see an effective decoherence-free interaction. I remember like the one I showed in the case of single cavity modes. And the answer is yes. But now the shape of the interaction potential is now more interesting. So if I couple two atoms I and j, then it can be generalized to an arbitrary number of atoms. This is the coupling strength now. Remember that with the cavity mode that was constant, independent of I and j. Now you see it goes, it decreases with the distance between the two atoms. Okay, because these I and j are the cavities directly coupled to the two atoms, and this is reasonable. Like it is reasonable that the more distance, if the atoms are very distant far apart, right? Each one will interact with the cavities if we were alone. Okay. So it's reasonable that this should depend on the distance. And of course, I'm not proving this result, but let me just comment on the importance of this, which people realized, I think, about 10 years ago. The importance of this result is that this is the one important point is this. So you see that the decay with the distance is exponential, and the typical interaction range, right, is lambda here, scales this way, scales as 1 over square root of the detuning in particular. Okay. Now this means that if delta gets smaller and smaller, right, that means that the atomic frequency is closer and closer to the band edge, right? Then lambda will get larger and larger, right? And so the interaction range will get larger and larger. Okay. Now the interesting thing from an experimental viewpoint is that tuning delta is usually very easy in labs, even here at TPFL. Right. So this means that, and this is a big difference. This is a big difference from the cavity. Because now, if you tune delta, which is easy, right? That means that this way you can tune the interaction range between the atoms. Okay, this is the interesting property. Recently, it was shown in this paper that this possibility allows you can be exploited for quantum information processing tasks, and in particular for, in this case, for variational quantum simulator.
A quick question.
Yeah.
You said that you are now taking the thermodynamic limit in this calculation.
Yes.
But
yes.
how many modes do you need to approximate the system with this immense scaling?
How many modes?
Yeah. To approximate.
Well, I would say that G should be larger than the frequency spacing between the nodes, right? Because otherwise it means that the qubit is seeing only one mode at a time if you tune inside the band. Here the guys are more expert than me on this, probably. But we can discuss.
But it works very similar if you also have a discrete spectrum, not a continuous.
Yes, but he's asking when the discrete one approximates well the continuous one. Okay. Okay, now, this is the result. My next main task of this talk is showing why this result is related to occurrence of so-called atom-photon bound states, which is in the title of the presentation. Okay. So let me introduce what atom-photon bound states. I will carry out this task using a very general model. Okay. Very general model where this is just some technicalities. This kind of generalization of the previous Hamiltonian, where now I have a generic photonic bath, which can be even a single cavity or a couple cavity array, or like a network of cavities coupled to one another. And this JXX prime is the hopping rate within these network cavities. Okay, and the coupling is local in these, This is just notation. In this kind of systems, including all the ones I've been talking about so far, you have conservation of total number of excitations. That means that, right, for instance, if I have a state where the field is in the vacuum state and the atom is in excited state, I say that I have one excitation, but these are one excitation state. I can also have another one excitation state is a state where the atom is in the ground state, but now I have cavity X excited in one photon populating cavity X. Okay, and it's evident that due to the rotating wave approximations, which is why you see there are only counter-rotating terms in the interaction Hamiltonian, the total number of excitations is conserved in this kind of systems. These are important points. And in particular, in the single excitation sector, is a sector which is spanned by the following basis. You either have either the state where the atom is in excited state, you have no photons, or the state where the atom is in the ground state, you have one photon populating cavity X. Okay. And I will use throughout this very simplified notation, I will call this guy just E, okay? Meaning that I have an excitation sitting on the atom, or I will call, in this case, I will call this guy X, meaning that now I have only one excitation sitting on cavity X. Okay, now a general single excitation rest state. Of course, you can have, people call rest states eigenstates of the total Hamiltonian of an atom field system. Okay, I will be particularly interested because this is sufficient for our goals to rest states living in the single excitation sector. In this case, the general form of a rest state like that is this one, where you see that these are superposition of E and G psi, where this small psi is a single photon state. Okay, single photon state, meaning that you see it's a superposition of one single photon state living in cavities labeled by X. Okay, and these are eigenstate by definition of the total Hamiltonian. Okay, and people say that the atom is dressed by a single photon. This is just another saying. Now, just one quick comment. If you think now of a large photonic path, even the couple cavity array in the limit of infinite number of cavities, okay, this dress state in most cases will be unbound dress state. By unbound means like non-normalizable, so something like a plane wave in some sense. Okay, for a single atom, it would be, for instance, one possible dress state. Unbound dress state is a state describing a scattering process where a photon scatters from the atom. Okay, and these are the typical dress states that probably you expect to encounter with a large photonic path. But the point is that even when the path is thermodynamically very large, okay, you can have situations in which bound atom-photon bound state appears. So the strict mathematical definition of an atom-photon bound state is that it is a dress state which is normalizable, and that means that if the path goes in the thermodynamic limit, then this state remains normalized. Okay? Right? Because if the path is not in the thermodynamic limit, then of course all dress states are normalized. Okay? That's of course just to appreciate the definition, the property. Okay? And then if this is normalizable, it can be written in this way, where this n now is truly a normalization factor. And of course, that means if it is normalized, that means the psi is partially localized state. That's the point. Okay. So in order for the state to be normalizable, the photonic component of the dress state must be localized on a finite region of space. Okay. Otherwise, that couldn't be normalizable. Okay. So, for instance, a so-called scattering state describing the scattering of a photon from an atom, that couldn't be a bound state. Okay. So let me just quick mention two examples of bound state. Let me start from in some sense these are trivial example, where the bath is just made out of a single cavity, like the one I talked about before. Okay. Of course, here taking the thermodynamic limit wouldn't make any sense. It's just a single cavity, and of course, stress states here are normalized, so they are bound, trivially bound. And these are the two familiar, maybe to some of you, stress state of the Jennings-Cummings model, where you see that you have a superposition of the excited state of the atom and excited state of the cavity. Now I'm calling this guy V, just for notational purposes, and these are the two energies. Okay. This is a case with zero detouring corresponding to vacuum rapid oscillation. And you see that these are the two dressed energies. And this is the case in the dispersive regime, where you remember that this was the case where the detouring was very large. Okay. When the detouring is very large, you see that this is very similar to a heteronuclear biatomic molecule. For some of you might be familiar with this topic, where you have this the atomic frequency, the cavity frequency, and despite they are coupled, you see that the stress states are not very different from these frequencies, and so this state is mostly atomic, and this state is mostly photonic. Okay, and the mostly atomic state is this one here, because you see that when coupling is very small, when G over delta is very small, then this term here will have a dominant contribution from this one, and so that means that the atom is slightly, someone would say, slightly dressed by the cavity photon. Okay. Now, what about the atom in the coupled cavity area, where you remember that I already stated that here you can have these interesting de Green's free interactions between atoms, which have, you remember, the exponential shape. Now, bound state instead, of course, in this case, and this is less trivial, some sense, because of course, even when the number of cavities is very large. So to let you develop some intuition of why this atom photon bound state arises, there are many ways to say that. So, for instance, think of having the atom out of the band. And for a second, imagine that G is 0, so this trivial case where the atom is fully decoupled. Then it's clear that you have a stress state, which is just the atom in the excited state, right? And yeah, I think I miss. And the frequency of this bound state will just be the same frequency as the atom. Okay, this is trivial, right? Now, if you imagine to turn on the coupling just a little bit, right? I mean, there is no way to expect, you are far from the bound edge where something weird can happen. I mean, there is no reason to expect that this state should change significantly. But the only thing is that, as is reasonable, it acquires a little photonic component, okay? And it remains normalizable. It must remain normalizable, I mean, if it's reasonable, right? If you increase the coupling a little bit, okay? Now, how does this photonic component look like? It looks like, this can be proven in various ways. This is easy. It can be proven that it has this exponential shape. So you see it's exponentially localized around the atom, okay? And importantly, this localization length, right, which measures how spread in space is this atom photon bound state, is exactly the same guy as the one you saw previously for the de Green's free interaction between the two atoms coupled to the array in the dispersive regime. They just have the same shape. Okay? So what I'm observing now is that the de Green's free interaction potential inherits the same shape as the single atom, because here I have only one atom, bound state. Okay? And I'm going to provide some more evidence now next of the reason why this happens. Maybe just another very quick comment. How much time I have left?
Still 25 minutes.
Left?
Yeah.
A lot of time. Okay. Normally at this point, they would stop me already. No, I'll try to make it shorter. Maybe some of you is familiar with the impurity problem in condensed matter. That's a very well-known problem. This is very similar to an impurity in a lattice. When you have an impurity in a lattice and the impurity energy lies in the band gap, right? You can have formation of a bound state having exactly an exponentially localized shape. And it's not exactly the same thing, but the two problems are very much connected. This is something we also worked on in the past. Now, connection to fractional decay. Remember that in the lattice we had this possible decay of the atoms. So let us now see what happens in terms of the bound states. Right? When I have my atoms here G is very small. Okay. What I expect here is that the atom photon bound state will arise. So, sorry, just a preliminary comment. The occurrence of this atom photon bound state, okay, somehow allows you to explain why the atom cannot fully decay into the bath. Okay? Because what happens when you excite the atom is that you expect that it will have an overlap over these atom photon bound states, right? The one that I talked before. You will have an overlap on this photon bound state. Okay. And now this bound state cannot propagate across the lattice. Okay, and this roughly explains why you have fractional decay. So the atom cannot fully decay into the lattice. And you see that you might remember that when in this case here, where the domain was larger, you see that I almost had inhibition of emission. And the reason why this happens is that here the atomic component, namely a component of a state at E of the bound state, is dominant. Okay. While here with slower detuning, right, it's reasonable that when I put the atom closer and closer in frequency to the band edge, the atom will get more and more dressed, meaning that the photonic component will get larger and larger, and the atomic one will get lower and lower. Okay. And so that's why in this case the existence atom photon bound state fully inhibits decay, whereas here it partially inhibits decay. And what you're left with in the end, this is easy to show, is that this asymptotic excitation of the atom is just the same as the overlap of the atom over the atom photon bound state. It's just the same. So it is as if this means that it is as if all the photonic, all the excitation, all the initial fraction of the atom excitation over unbound dry state is washed out in the end because this flied out, and you are left only with the atom photon bound state component. What about this case here? This is also interesting for giant atoms. If I have my coupling weak and I move the atom inside the band, okay, here I don't expect to see any bound state, okay. And in fact, so this here in this case no bound state occurs, and in fact in this case I have just exponential decay going on, so full dissipation. So for this system, I want to stress that for this system, it is important that in weak coupling, this should be said, the bound state, the atom, in order for the bound state to arise, the atom should be out of the band. Okay. With stronger coupling, this can also be happen, but so long as weak coupling, so in this case means G much smaller than J is involved, it is important that the atom is, let's say in general, not far from the edge. So either in the off the band or anywhere not far from the edge. If it is well inside the band, then no bound state will arise with a standard atom like this. Now, just a few words on the weak coupling limit of this bound state. This is just, I already said that, in fact, so I will go very fast here. So this is just what happens when when the atom is far from the band edge, and the coupling is very, very weak. It's easy to see that this is just an instance here. This is true on a general footing. That if this bound state exists, this is not obvious. Then to the lowest order in the coupling strength, this will be the general form it has. So you see that you have this guy here, and then this guy going like the first power g. And to the lowest leading order, the frequency of the bound state is the same as the atom. Okay. Now apparently this state is not normalized, but in fact it is, because it's normalized if you neglect second order terms in g, like terms like g squared. Okay. That's a very important point for the coherence-free interaction. Okay, now I'll be quicker, I think. Once again, if I take the previous model, you remember I had this model of a general photonic path, an atom couple under rotating wave approximation to these general network coupled cavities. I can generalize this model to a set of atoms. You see now I have atoms labeled by J. Okay, and let me assume again that the atoms are all the same. And now I hope most of you are more or less familiar with Limblad-Massier equation. If you are in the so-called Markovian regime, which, I mean, defining what is the Markovian regime is not super obvious, but let's say that typically you require weak coupling, right? And also you require to stay enough away from fast singularities, which in the case of coupled cavity array means that you should be not too close to the edge. Okay? Then what happens is that you can trace off the field degrees of freedom. I'm assuming here that you are at 0 temperature. Okay, you can trace over the field degrees of freedom and end up with an effective equation for the atom state, many atom states in this case. Okay. And this effective equation is this so-called Massier equation. Is a generalization of the Schrödinger equation in the language of density matrix. And it features two terms. One is the so-called dissipator. Okay, this describes, this is the reversible part of the dynamics, and this describes the coherent part of the dynamics, and the generator of this dynamic, of this guy here, is the effective Hamiltonian between the atoms. Okay, you see that once again I have the coupling strength J prime here, and somehow you can think of these two terms in this specific context as coherent interactions between the atoms, coherent dipole, some people would say coherent dipole interaction between the atom, and incoherent dipole interaction between the atom, coherent and incoherent. So what happens when you have a decoherence-free interaction is that you can realize conditions such that for some reason you get rid of this part. And you're only left with the coherent interactions, which must also be non-trivial. I mean, you'll see what I mean very shortly. I mean, you don't want to both this guy and this guy to vanish. You want this guy to vanish and this guy must be non-trivial. Okay, these are just general expression, but don't worry too much about that. For this KJ prime, these rates appearing here, and these are expressed in terms of the Green function of the field. Don't worry too much about that. I just want to say that these guys depends. So this guy depends only on the Hamiltonian of the field, the Green function of the field. I just want to stress here that you see that these sandwiches appearing here are between xj and xj prime. What are xj and xj prime? What I will call side states. Side j is just the state where a single photon lies at the cavity directly coupled to atom j. That's very simple. So xj in some sense is the atom position, and xj, this guy xj is just the single photon state associated to that cavity. Okay. This is apparently a minor point, but it will play a role when you generalize to German atoms. And now theorem, we formalized a theorem recently, I mean, which is actually not difficult to prove once you set up all the formulas. It's just one line. Okay. But I think for the first time we really focused on this property, focused well on the connection between the gradients free, namely this guy vanishing and atom photon bound state. So it can be proven that if this guy vanishes, okay, namely all these rate gamma are 0, then this happens if and only if each atom seeds. This is not obvious because, as I said, the bound state may not exist. If and only if, under weak coupling, each atom seeds an atom photon bound state. Okay. If this is true, then the dynamics, the dissipator vanishes. Okay. Also, this is how and that's the key point. This is how the coupling strength look like. These are remember, these are what I also call the interaction potential between the atoms. Okay. This was the guy that was constant, independent of J and J prime for the cavity, and which had an exponential shape with the array. And you see that this guy is essentially proportional to this sandwich here. This is the overlap of the bound state of atom J prime, meaning bound state seeded by atom J prime, as if atom J prime were alone, and the only one coupled to the lattice, to the path. And you have here the overlap on the side state associated to the position of atom J. Okay, that's the key point. So this connects the interaction potential to overlaps of bound state. And now everything should be probably hopefully clear. This suggests the following picture, which is kind of intuitive, I think. You have your lattice. I mean, this is just standard lattice, it could be anything. And you now come, the first atom comes in and coupled to this cavity here. Okay. And because of that, if an atom photon bound state is generated, now when you come with a second atom here, if the amplitude of the bound state seeded by the first atom on the site where you put the second atom is non-zero, okay, and then the second atom will see there is a bound state generated by the first one, and as a consequence, the two atoms will couple to one another with this coupling rate, which in fact goes like the overlap of this guy with this side state of atom J. Okay. Of course, it may also be that the atom is very, very far apart, and so in this case, the interaction will not take place.
But will it also decay exponentially? This overlap?
This one?
Yeah, the function.
Can you repeat the question also?
Yes, he's asking whether this indicates exponentially in the case of a couple cavity array. Yes, because this is essentially telling you, and this actually brings me to the conclusion of this slide, that the shape of the interaction potential and the shape of the bound state wave function of a single atom are just, in fact, the same thing. Okay? So studying the covariance-free interactions and studying single atom photon bound state is in fact the same thing. If you search for atom photon bound state, then you search for atom covariance-free interaction in the other way around. Okay. Okay, I'm now in the final part. Let me just mention what we did with giant atoms, what we understood with giant atoms. So what is, as I said, right? Remember in the beginning I said the giant atom can couple non-locally to a path. Okay, that means that if you have an atom here, you see that another atom can couple, for instance, in this case, to cavity 0 and cavity T. And we say in this case that we have two coupling points, one at cavity 0, one at cavity T. I mean, this brings in interesting effects and new effects compared to normal atoms. One, certainly very important one, is that now the atom, because of the fact that it has more than one coupling point, can exhibit self-interference effects. Okay. So for instance, you remember, and this is what I'm more interested in here, you remember that I said when you have a normal atom coupled to the middle, to the inside the band. Under weak coupling, no bound state arises. Okay. And now the interesting thing is that when you have a giant atom, even if you couple it to the center of the band, even under weak coupling, there are conditions such that a bound state can arise, despite it is in the band. And in fact, this is what some people call bound state in the continuum. There is a whole huge photonics literature studying bound state in the continuum.
Before the invention of
Yes,
the
yes. I think the first paper showing bound state in the continuum dates back to the 30s, I think. So, yeah, this can happen. My bound state not necessarily lies out of continuum. They can also lie inside. So there is no fundamental reason to say that they must lie out. And actually, you can maybe understand this with a giant atom, because what can happen here is that an atom photon bound state can arise, and somehow it's different from the one I talked previously, because these are pure interference effects. It is very similar to what you see, for instance, with Fabry-Perot resonators, or if you want, you can. So you see that depending on the in fact, what happens is that depending on the distance between the lead, okay, and the frequency of the atom, right? Because to the frequency of the atom also corresponds to a certain wavelength of light. Light almost resonant with the atom. So if this light is such that, I'm really describing this in very simple words, if this wavelength is such that a stationary wave can form within the two coupling points, then you can have a bound state where you see that the photonic component will look like this and will be strictly localized between the two coupling points. In this case, where the atomic frequency lies inside the band. This is very easy to prove. Now, based on this effect, people asked not so long ago, and what happens with many giant atoms? You can already also maybe expect, based on what I said before, that if you can have bound state in the continuum, then I can also have de Green's-free interaction in the continuum. Okay, and this is true. And this was first predicted. I think the first time we heard this was in the first waveguide QED workshop, which Shingo attended in 2018, where Anton Koglum said about this talked about this nice result, and 2 years after it was tested successfully at MIT in this experiment in a circuit QED setup. And this is quite striking because normally, what we are saying here is that if you have two atoms right in the middle of a band in the continuum, normally with normal atoms, as I said before, you have coherent dipole-dipole interaction and incoherent dipole interactions. And it's easy to see that it's impossible to get rid of incoherent dipole-dipole interactions. And this is what you can do instead with giant atoms. How can you accommodate? Just a quick remark. Nobody until recently explained these things in terms of bound state, even though it was in the air somehow. How can you explain this in terms of the theory I explained before? So now you have once again a general, I will not give equations here, you have just a general photonic path. Now the atom is coupled bilocally to more than one cavity in general. Okay. And it's easy to see that you can map this atom if you make a unitary. You can go in a picture where the atom becomes once again a normal atom. By normal atom I mean local coupling. But the cost of this is that the path is no longer, it can get more complicated and even lose some symmetry sometimes. Okay. So this means that I can define, even though the atom is non-local, I can define a fictitious atomic position, which is this guy here. So just a very simple instance, if I have this atom coupled to two cavities and these coupling are the same, then this fictitious side state will be just the symmetric superposition of the two cavities to which the atom is coupled to. Okay. This allows you to define kind of fictitious position, which could also be complex. I mean, This guy could be complex, and then in this case, here you will have a complex phase factor. Now, the previous theory I discussed, right? The previous theorem can be general. Once you set up the formalize this way, it can be generalized very easily. Okay. And once again, you can show that the dissipator vanishes if and only if each atom sits an atom-photon bound state. And you are only left with an effective Hamiltonian degrades free. And again, the interaction potential can be expressed like the overlap of the bound state seeded by each atom, but now on this fictitious position state, side state of the other atom. Okay. I think I have the last 2 slides left, so you can start relaxing. In the MIT experiment, they verified something that was. There is some shock. Well, no.
On the right.
MIT experiment. So when this effect was first predicted, it was shown that you can if you have 2 atoms coupled to a waveguide, you can have like this configuration. I hope you can see this. This is called serial. So in this case, no degrades-free interaction was predicted and observed. Another one is a so-called braided, which is like this one. Okay. And then you have yet another one, which is the nested, right? And out of these 3 configurations, braided, nested, and serial, braided was the one predicted to exhibit degrades-free interactions, and this was tested in the lab. And now, if you use these in this picture here, right? In this picture here, now you can see this immediately. I think that people, to my understanding, missed a very simple way to explain this. Why? Right? It depends on the configuration, and also, most importantly, how can you generalize these properties to more exotic photonic lattices, even 2D or something? Now this is very easy to explain, because in the braided, for instance, in the serial configuration, it's clear that there is no overlap. Right? I said that the bound state lives inside the 2 coupling points, so it's clear that in this case, no overlap of this bound state can occur with this one. And also in the nested one, because this guy has coupling points external to the bound state, but then you need the braided. Okay. Very simplified explanation, and there are some subtleties, but roughly speaking, that's the idea. Because this is the only way such that you can have this overlap giving rise to this effective interaction. Now, based on this, you can also go to 2D. So very briefly, you also can also make 2D example. So, for instance, you can have a giant atom with 4 coupling points coupled now to a 2D photonic lattice, which is just a 2D generalization of the coupled cavity array. And then this guy, 1, 2, 3, and 4, these are the 4 coupling points. Okay? And you can show that there exist conditions such that a bound state, an atom-photon bound state in the continuum arises. Like these are the colors for the amplitude of these atom-photon bound states. And again, you can have braided and in this case nested configurations. Right? In this case, right, these like 2 interspersed. 1, 2, 3. This is one atom. This is the other atom. These also can give rise to degrades-free interaction. Even in very exotic systems, these are theoretical prediction. These are a leap 2D lattice with the nearest neighbor interactions. One nice thing is that here this is 2D, and the coupling point has the giant atom has 2 coupling points, and still you can show that these are all destructive interference games. Still, the bound state can arise and live in between the coupling points. And you see that it has a linear geometry despite you are going 2D. And again, you can have occurrence of decoherence-free interaction when this overlap is successful. Yes, with this, yeah.
For the nested version, the bound state of the outer giant atom would couple to the inner giant.
Very good question. Very good question. I said there was a subtlety. Okay, there is a mathematical way to get out of this because it must be right. If you look at this, if you look at this guy, right, this of course lies out of the bound state of the first, which will lead, which tells you that the interaction is 0. Of course, I can also reason in the opposite way, in terms of the bound state seeded by the other one. Okay, but of course the result must be the same. This you can show from the Hermitianity of the effective Hamiltonian. So you cannot reach a different conclusion if you reason in terms of the bound state of the other one.
Yes.
Okay, but I mean these are good questions because then one asks, how is it possible that if I now look at the bound state generated by this one, right, then the legs of the first one are inside the region of the former one, okay? But you can show that, I mean, as I said, each atom must ensure the existence of a bound state, okay? And this imposes a condition, okay? This condition is such that you find that, as it must be, the overlap is also 0 in this case, okay? So it is true that in this case, the legs of the first one are inside this one. But remember that you have to ensure that this is the right. This is the overlap I'm talking about, and the overlap is a superposition state. And the two things cancel in such a way that you get 0. Okay, just final thing. I didn't have to discuss about that because it would have taken a lot of time. I mean, we have also a general way criterion to guess existence of new bound state, okay, which was what we did for guessing, for instance, this system. And this is based also on vacancy like that stated up here, and there's a reason why these states are called like that, which we proposed years ago for normal atoms and can be generalized to giant atoms. Okay, let me now thank collaborators. The first 3, Shwezan Tsun, Luca Nunforte, who is now back in Palermo, and Angelo Carollo, my office mates, are the main guys in the crew of the project of this paper I've talked about most of the time. But also let me mention other people with whom I collaborate a lot on this topic. Enrico Di Benedetto is in the audience, and Alejandro Gonzalez Tudela, who is a major expert and even pioneer of the field. Unfortunately, I didn't have time to discuss about this. It's very interesting to study what happens when you have atoms coupled to flat band. You can, if you're interested, you can find this in this paper. Just a few words, because I've been talking about band and a single cavity, and a flat band somehow it's something in between. Okay, because a flat band it's a band which is dispersionless, so just a single frequency. Okay, and this is like a cavity where you have just a normal frequency, but at the same time, the flat band has a thermodynamic degeneracy. Okay, so it's which is like more like a band of a lattice. So somehow a flat band is something between a cavity and a band. I'm also indebted, looking at a longer time scale, to Giuseppe Galloia and Peter Rubble for my understanding of these topics about atom-photon bound state. And more recently, let me also acknowledge Dominic Schnabel, who is an experimentalist at Stony Brook. He works with ultra-cold atoms, and he made one of the first experiments showing existence of an atom-photon bound state like those I've been discussing. And it's an interesting implementation where ultra-cold atoms somehow emulate both emitters and the field. And if you're interested, we recently wrote a kind of general short overview on the field, including these topics. And these are just some take-home message. So atom-photon coupled to It consists of a bound state, just to summarize. Bound state can mediate Lagrange-free Hamiltonians on the wave coupling. So bound state can give you Lagrange-free Hamiltonian, but somehow show you also that the other way around. That if you have a Lagrange-free of dynamics, then each atom, this can occur only when each atoms generate bound state. And if so, when bound state overlap atom sites, then a non-trivial Lagrange-free interaction, of course. And finally, about giant atom, a giant atom can see bound state and Lagrange-free interaction, which are unattainable with normal atom, and in particular, bound state and Lagrange-free interaction in the continuum and in 2D. And with this, I thank you very much for your attention.
Thanks a lot, Francesco. There were already many questions during the talk, but if someone wants to ask, you can ask any further questions.
Meanwhile, can I read some more?
Yes. Yes. So is there any other curiosity question? Yeah.
I have a question about 2D lattice case. I think it's kind of easy to understand to have a dark state or decoherent substate in 1D. But I'm not sure we can get a dark state in 2D.
Yeah, this counterintuitive going can
So
happen.
can you make the
Yes.
Yes. to get the dark state in 2D?
It's well in this case, I think here it's kind of even trivial, because what happens here is that when you it's like having a 2-1D thing when you go, because this happens at the center of the band.
We need just four qubits to
Sorry?
get at least you need 4 qubits to get.
Yes, four.
We cannot make a dark.
No, in
state.
this case with 2 you cannot make it,
Okay. You need 4.
which makes it a bit more intuitive.
Yeah.
With 2, but still with 2 you can make it, but you have to make weirder lattice, like the one I showed. Yes.
Yeah, so you said that for a giant atom, the bound state lives within the 2 coupling points of the giant atom.
Yes.
Is it true with a finite size array?
No. Here the array could be infinite.
Yeah, I guess here you consider an infinite array,
Yes.
right? But if you have some finite size effect, do you expect to have some leakage outside of the 2 coupling points? And maybe related, if you have some periodic boundary condition, for instance?
No, I think this is unrelated. I think you're gonna have it even with a finite size array. I mean, the essential point is that you can have a standing wave, right? If these are the 2 coupling points, right? And you imagine to cut out that part of that chunk of lattice from the remaining, then there must be a normal modes of the existing.
Yeah.
I think this is possible even with I think this is possible even with finite size array.
And now if you would put it on a ring, like if your finite size array has periodic boundary condition, and you couple a giant atom,
You can still have it.
it could go both ways.
Yes.
Fascinating.
No, actually, it's important that it goes both ways, right? Because it's similar to formation of a standing wave. So you must have interference between a right propagating and a left propagating wave. That's not weird. That helps.
Yes, please. Yeah.
I have a question, might be a bit weird, but if in all you said, I removed the 2-level system and I just put a bosonic mode, I don't know, a resonator, whatever you said remains somehow
Yes.
valid?
Yes, it remains true because I'm looking at the 0 temperature regime. So everything in fact remains the same. Yes. If I would look at higher excitation dynamics, then this would change. But this, I mean, like the Limblay mass equation, everything assumed that the bath was in the vacuum state. So it will remain. You can just replace the spin ladder operators with the bosonic ones for sure.
You can do anything, but will be for application will be useless in this sense.
Sure.
But
But
you
he
can
just
study it,
asked
so yeah.
whether
All
remain.
the effects remain the same.
Yes, it's the same.
Are there studies including terms that do not concern the number of particles, such that, for example, the counterfeiting terms, such that, for example, the dress state you explained here was a state with a total number of number excitations equal to 1. But maybe if you include the counterfeiting terms, you may have a very general dress
Yes, they
state.
studied concerning the atom couple cavity array, the exponential one. They studied how the exponential one generalizes to ultra-strong coupling. David Zueco, whom you probably know, David Zueco and Garcia Di Paul studied this. This was studied. But I have to say that many, like for instance, the interference mechanism behind these giant atom things would not. I don't think it would work. Because this requires excitation number of excitation. Is this pure interference?
So it will be affected by this.
Yes.
Okay.
Yes, it would.
So in the interest of time, because we are already out, let's stop here for the moment and thank again Francesco. But then